Hi guys, this is Mrs. Foy, and I am so excited to talk to you today about the effects of polarity. So you guys have been practicing now for a while with recognizing polar molecules and understanding what a polar molecule means and a polar versus a nonpolar molecule. So today we're going to talk about what that means as far as how the chemical acts. And that's important, that's powerful for a chemist to be able to do that because we like to be able to predict. So understanding about polarity is going to help us understand a physical property like solubility. So for example, the idea that if you spill a greasy piece of pizza on your nice new shirt, just putting a bunch of water on it is not going to help, right? Because the water is polar, and that the lipid, greasy, cheesy pizza is nonpolar, and so the water is not going to do anything to get rid of that pizza. You would need some nonpolar soap for that to happen. Polarity is also going to help us understand melting points and boiling points, right? To be able to understand why a chemical substance would go from a solid to a liquid to a gas, and that's important. And also properties like surface tension. And so hopefully we're gonna get to the bottom of that today. So let's talk about molecular compounds, covalent compounds. And we have already talked about the idea that what makes a covalent compound is the sharing of electrons between atoms. And so we would call this an intramolecular force, forces within the molecule. You might remember when you were a freshman, your biology teacher talked about intracellular organelles, like a mitochondria or a nucleus. And you know that that is stuff inside the cell. So these bonds that we're talking about here are the bonds that are the sharing of electrons within the molecule, holding the atoms together inside of a molecule. The difference between this word that I'm going to use now is very subtle, but it's extremely different, and you need to make sure that you understand it. Intermolecular force is a force between molecules, and inter means between, not within. So think of an international flight is going to go between one country and another country. So we have another name for these in chemistry. We call them van der Waals forces. So an intermolecular force is a van der Waals force, and we're going to see there's three different categories of these. So these forces, and I can see one right here, I can see one right here, I can see one right here. Sometimes it helps to recognize the molecule. This is water, this is water, this is water, right? So I'm looking at the various water molecules, and the force that I want you to look at now is in between the different water molecules, and these are called van der Waals forces. You learned about these when you were a baby freshman too, because you had to learn about hydrogen bonds, and hydrogen bonds are one type of van der Waals force that we're going to talk about actually at the end. But these forces that you can see here are going to be very important. These intermolecular forces are very important with phase changes, right? So when we talk about a phase change, we're talking about something that is going from a solid to a liquid to a gas. And just to remind you that when substances are in a solid, they're lined up like little soldiers, like in an array, right? The distance is not very great between the molecules or the atoms. In a liquid, we have greater movement, and we have more distance between these, more attraction. And in a gas, these guys are moving really fast, and they're very far apart, and there's very little interaction between the molecules. So this is going to become important, these intermolecular forces with phase changes. So I want you to make a prediction here. Which of these would have a stronger attractive force between the molecules? So let's look at carbon tetrachloride, right? So I've got my shape here. Here's my Lewis structure, right? And so here is my Lewis structure here. I'm being lazy and drawing my lone pairs like this, which is okay. You'll see some textbooks that do that. And so I can see that this molecule over here is very nonpolar, right? That molecule is very nonpolar. But over here, I can see that I am going to have some polar molecules, some polar intramolecular bonds that I see here. And when I look at the whole shape of the molecule, I can see that there's going to be more pulling of the electrons down towards the chlorines, and not as much up here where the hydrogen is. So I would guess that because this is a polar molecule, I'm going to have greater attraction between this molecule and another molecule like it, right? Because it's going to have a negative and positive end, and I know that negative and positive ends are going to attract each other. So we're going to talk about the types of intermolecular forces, van der Waals forces, and the first one is the weakest one. And this one is called a London dispersion force, a London dispersion force. So let me just explain this. So in a London dispersion force, I want you to imagine this helium atom, and it's got its 2 electrons buzzing around in its electron cloud. But because these are moving and they're random motions within this orbital, at any given point, the 2 electrons might end up on one side of this electron cloud versus another. And so at that instantaneous point, this end of the helium atom is going to be slightly negative, isn't it? And at that point, if this helium atom comes into contact with another helium atom, electrons don't like each other, do they? And so in that instant, those electrons in helium atom number 1 are going to go whipping over to the outside, away from the electrons from the first. And so sometimes we call this an induced dipole, because one atom has induced a dipole on the other, but we know that they are momentary and they are temporary. And so we might draw them like this, right? So we have a slight positive charge and a slight negative charge where the electrons ended up over that side, and the same with the helium atom number 1 now that was induced by the random movement of the electrons in the first atom. And so because of this, there would be a very weak intermolecular attraction between the negative end of helium atom number 2 and the positive end of helium atom number 1. And that is called a London dispersion force, or sometimes just a dispersion force for short. So dispersion forces are very weak. They're not very strong. Nonpolar molecules and non-metallic elements are only held together by dispersion forces. So all of these molecules, all molecules are going to have at least they will have London dispersion forces, but they may be very weak. So the shape of the molecule and the size of the molecule affects the London dispersion force. So here we have 2 long, skinny molecules, and I can see that these long and skinny molecules are going to have a lot more real estate to have these London dispersion forces. And so they are going to have a slightly greater attraction. Remember, we're talking about an intermolecular force, right, between these molecules. They're going to have a stronger attraction between these two molecules than shorter fat molecules. And that's going to lead to a higher boiling point. Do you understand why that is? Because remember that if we have, and I could also say it would lead to a higher melting point. Remember, solid, liquids, and then gases are super, super far apart. So here in a solid, I would have the intermolecular force would be stronger than it is in a liquid than it is in a gas. Okay? So that is why phase changes depend on these intermolecular forces. So what about if you had two of the same chemical formula? Which one would have a stronger dispersion force? So here we have two different structures of a type of a 5-carbon hydrocarbon chain. Here is pentane, and this is a structure called neopentane. Well, this one is longer than skinnier. This has more, like, you can think of it as like surface area of these interactions between one molecule and another molecule. And so this one is going to have a greater London dispersion force than this shorter, fatter molecules are going to have less. This would have greater, this would have less. So we know that shape has a difference, and also mass has a difference, right? So the more atoms, the more electrons, the more London dispersion forces, right? So the more the more a molecule weighs, then it's going to have more London dispersion force. But the shape of it, of course, makes a difference, as we just saw. All right, so here we have, again, 3 different molecules, 1, 2, 3, 4, 5 carbons, 1, 2, 3, 4, 5 carbons, 1, 2, 3, 4, 5 carbons, and we have the same weight, right? These would weigh the same. What's different is that the shapes, this is long and skinny, so this one would have the greater surface area, right? So it would have greater London dispersion forces between different molecules of that molecule, right? They would be held together with a little bit more force than this one, and then this would be the least. The short fat molecule will be the least London dispersion force. All right, so now let's see if we can figure out which of these molecules would have the greatest boiling point. So I'll give you a chance to think about this. Looks like I've got the same 1, 2, 3, 4, 5, 6, 7, 8. So I've got 8 carbons, 1, 2, 3, 4, 5, 6. This only has 6 carbons, 1, 2, 3, 4, 5, 6. This one has 1, 2, 3, 4, 5, 6, 7, 8 carbons again. But this one, octane, is going to have the most London dispersion forces, isn't it? Because it's long and skinny. So if it has the most London dispersion forces, it should have the higher boiling point. This one would have a little bit less because it's a little more clumpy in the middle. It's not quite as long and skinny. So this one would be this boiling point. And this guy right down here would have the least London dispersion force because it is less heavy, right? There's less, the molecular weight is less. There are less atoms, therefore less electrons, and it's shorter and fatter. So that one would have the lowest boiling point. All right, so now let's look at these halogens, and I can see that they are in increasing order of molecular weight. And yep, their boiling points are going to increase as well, right? So the increased molecular weight is going to increase the dispersion force. The stronger dispersion forces means more attraction between the different, in this case, diatomic molecules which would mean that it would be harder to turn them into gas. Again, let's take a look here. Which of these would have the higher boiling point, neon or krypton? Well, here's neon, here's krypton, here is a molecular weight, here is this molecular weight, and it makes sense, right? Look at the boiling points. Krypton has a much higher boiling point. That's because krypton has more London dispersion force because it has a greater molecular weight. It's got more electrons and therefore more opportunity to have those temporary dipoles formed. So now I want to talk about another type of another type of van der Waals intermolecular force called dipole-dipoles. And molecules that have a permanent dipole, in other words, a molecule that is permanently a polar molecule, is going to have a dipole-dipole interaction with another polar molecule. So these are not like we described before with the helium that just happen to have the electrons on one end of the electron orbital versus another. This is a polar molecule, right? So if I drew this, it would have the lone pairs would be around that chlorine. And I can see this is a linear molecule, but I can see that the it would be it's a polar bond, but it's also a polar molecule, right? So this would be the partial negative charge and partial positive charge. That's not temporary. That's not induced. That is a permanent, what we call dipole, because it has a positive pole and a negative pole. And so the positive end of this molecule is going to be attracted to the negative end of the neighboring molecule. This thing in green right here is a type of van der Waals force. It is a dipole-dipole interaction. And this is going to be stronger than the London dispersion force, right? It's going to be stronger. So here are some other dipole-dipole interactions. This dipole moment, you'll learn more about this when you take AP Chem, and this is just a quantitative measure of how strong the dipole is. So I can look at these different molecules, look how they're approximately the same molecular weight, but these are in increasing dipole moment. So that means that this acetonitrile is going to be a very polar molecule. And look what happens to the boiling points, right? So the more polar the molecule, the higher its boiling point. That is because it is going to have an attraction. It's going to have an attraction, an intermolecular attraction between the polar molecules, and that is going to tend to hold the molecules or atoms together, and it's going to make them harder to escape those that become a gas. So now we're going to talk about the last type of van der Waals force. So remember we talked about London dispersion force. So these are van der Waals forces or intermolecular forces. We talked about London dispersion force. We talked about a dipole-dipole force. And now we're going to talk about the granddaddy of all intermolecular forces, hydrogen bonding. So a hydrogen bond is a type of dipole-dipole, but it is the strongest intermolecular force. So here we have a hydrogen bromide, right? So I can draw my Lewis dot structure here. I know those are unpaired electrons there, and I know that I could draw my dipole diagram there, and I can see this is my electronegativities, and I can subtract them and say, yeah, this is there's a polar bond between those two atoms, but this molecule is polar, all right? But this molecule, we're going to see hydrogen fluoride, we're going to see this molecule is an extreme condition, and let's look. So here in hydrogen bromide, I have a dipole of 0.7. This is the difference between those. So I can see that if I have another molecule, I have to have at least two to be able to see any type of intermolecular force, right? So the negative end of this hydrogen bromide is going to be attracted to the positive end of another hydrogen bromide, and then I'm going to have the same thing here. So that's the regular dipole-dipole interaction. But in hydrogen fluoride, we have the special case of hydrogen bonding. And here is what we're going to see. When hydrogen bonds directly to fluorine, oxygen, or nitrogen, then we are going to have a situation where we could have a hydrogen bond form. These have to be bonded directly to those specific atoms, and the molecule has to be polar. So here I have an extremely polar covalent bond here, but I have an extremely polar molecule, right? So I can see that I have a the fluorine, is there anything more electronegative than the fluorine? No, right? So I've got some lone pairs there, but that thing is really pulling those electrons that way. And so what's going to happen is that if I have another hydrogen fluorine around, a hydrogen fluoride around, or a hydrofluoric acid, if this is an AQ, then what's going to happen is that the very negative end of this molecule is going to be very attracted to the positive end of another hydrogen fluoride, and the same thing with the positive end of another molecule being attracted here. And so these are called hydrogen bonds, and hydrogen bonds are the granddaddy of the van der Waals forces. And there we're going to see that these are very strong and definitely are going to affect the character of our chemical nature. So, as I've said, the hydrogen bonds are the strongest of all the intermolecular forces. We're only going to see hydrogen bonding when hydrogen is directly bonded to nitrogen, oxygen, or fluorine, and we have that huge electronegative difference, because remember, the fluorine is the most electronegative atom, and these guys are all up there in that corner of the periodic table. So it's going to create an extreme dipole, and those extreme dipoles are going to be attracted to the opposite charge of another molecule of that type. And those are what we call hydrogens. So you learned about this when you guys were baby freshmen. You learned about hydrogen bonds in water, and we know that that's why water reacts in, it's got the strange chemistry that it does, and that's why we have life on Earth. Is everywhere we have water, we have this, because water modulates temperatures, and it has some other properties that are very important for it. But here I can see that I've got these intermolecular forces here between the hydrogen on one molecule. In this case, this would be the dipole, the positive dipole here on one molecule is attracted to the oxygen end on the other, right? Because remember, I've got these lone pairs here, and oxygen's very electronegative. So hydrogen bonding, the strongest intermolecular force. And this is exactly where we're going to start off tomorrow. And so that's it. That's what I've got for you. And good luck, and I'll see you in class.